In episode 14 of the CySec101 training series, we are going to touch on networking concepts, and this is going to be the introductory networking room for the Cybersecurity 101 pathway of TryHackMe, and this is the very first room inside of the networking module. So we're going to go into some core networking concepts, and then as we go along this module, we're going to get more expansive, and we're going to talk about other concepts, security concepts, and then we're going to actually use some security tools that are very, very useful inside of networking. So first, we're going to have a word from our sponsor, and then from there, we're going to jump into the introduction. This episode is sponsored by the Hackaholics Anonymous membership community, which is the premier membership community for security professionals and hackers. And as a part of this community, you will get access to 4 tiers of benefits, and it starts with the supporter tier, which gets their own Discord server, as well as access to me directly and our advanced members, as well as early access to content, so on and so forth. And then there are the advanced members who get access to Python automations every month. They get access to live streams, exclusive content, exclusive downloads, very much like the Security Plus documents, as well as the practice examinations that we're going to be launching in a little bit. So to be able to join the Hackaholics Anonymous community, you can just go through the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@hankhackshackers/join, and then you will be taken directly to the join page. And I really look forward to seeing you in the community as well as in the Discord servers. And without further ado, let's actually jump into the networking concepts room. All right, so have you ever wondered why you need an IP address to access the internet? Is it true that an IP address can actually uniquely identify the user? Are you curious to learn what the life of a packet looks like? Are you curious to know what even a packet is, right? If you have any of those questions, you are probably a nerd just like me. And then you're going to get all of your questions answered inside of this room, as well as all the following rooms. This is going to be the first room in the networking module that's available for CySec 101. And in the very next video is going to be networking essentials. Then we're going to talk about the core protocols, as well as the secure versions of those core protocols. The prerequisites for this room and for this module are the pre-security path, which is like pre-kindergarten for people inside of the security and IT world. So I have done a lot of these videos, and they do exist on the channel. If you go to the earliest videos that are on the channel, basically the oldest videos that are on the channel, you'll get a lot of these videos available too. So offensive security intro, defensive security intro, what is networking, intro to LAN, the OSI model, and we're going to review a lot of these things again today. So if you haven't seen them, or if you don't want to go watch them right away, you're not going to miss much, because again, it's like pre-kindergarten for security. So we're going to review a lot of those things in the room today as well. But it is nice to get multiple exposures to these concepts, because it's a little bit easier to wrap your head around them. So if you've never heard of the ISO model, for example, then hearing it for the first time may be a little bit challenging, but it's not that bad, because again, we're just going to review these things in detail, and the more exposure you get to all of these concepts, the easier you'll wrap your head around them. The objectives that we have today are the ISO OSI network model, the IP addresses, subnets, and routing, and then the TCP, UDP, and port numbers, and of course, how to connect to an open TCP port from the command line. So that's going to be a practical exercise that we're going to run at the very end of this room. So let us get ready. Hopefully you're actually ready to go. This is actually one of the free rooms inside of TryHackMe. So anybody with just a basic free membership can deploy the virtual machines inside of this room. And then if you're interested in just getting the paid membership, it's literally $12 a month. And if you use the link in the description below, you will get a $5 discount off of that. So it'll make it even more accessible to you. So if you have not done so, definitely get yourself a membership to TryHackMe. Even if you just get a free membership, there's literally hundreds of rooms that are available for the free members. And then when you get into the paid membership, you just get some really, really dope stuff for the advanced teachings and everything like that. So that being said, let's actually jump into the OSI model. So if you've never been exposed to this, at first glance, it might seem complicated, but again, it's, just going through this repeatedly will make it click a little bit more. And I'm going to give you a couple of like cheat phrases that you can use to remember these things. And we'll look at some visuals to make it a little bit easier for you to wrap your head around it. And ultimately, I feel like you'll grab it fairly quickly. I think it's fairly easy, especially for somebody that's gone through it, that I had challenges. Now I know exactly how to teach it so that it makes it easier for you to understand. So we're not going to go super technical with this. We'll be conceptual so that you actually can wrap your head around it fairly easily. So ISO, which is the International Organization for Standardization, created the OSI model, which is the conceptual model, and it's more theoretical, and then we're going to talk about the practical model when we talk about TCP/IP. But the OSI model is basically the theoretical conceptual model behind communications across networks. So what needs to happen for my computer to talk to the YouTube server, and then what needs to happen for your phone or for your computer to get data from the YouTube server, and how do we actually establish this connection? What needs to take place, right? What are the individual steps? And what's really cool about this is that this happens in literally a fraction of a few seconds. So it's like it happens so quickly that it's kind of mind-boggling to wrap your head around the fact that these 7 steps, basically, these 7 layers, as we like to call them, they literally, it happens in a second. It happens in a couple of seconds. Now, it didn't happen like this at the very beginnings of the internet, because the internet was super slow around the time of America Online, right? So around that time, it was not fast. But right now, in the modern era of the internet, it's so fast for data to go through all of these layers that it's like, what is actually happening? So, it's good for you to understand networking. This is more for people who really want to be network admins and network engineers, that you would go into the depths of this stuff. But as a cybersecurity person, it's still important for you to understand this, because you will need to know what layers you have to protect, what protection actually means for each of these layers, and then, of course, how you would hack each of these layers if you actually were hired to be a pen tester or an ethical hacker. So, it starts with the physical layer being number 1, but then usually when you look at a visual like this, the application layer is actually the top layer. So we go from bottom to top in this model. When we talk about the TCP/IP layer, we're going to be going from top to bottom, and that's just another thing that they wanted to confuse us with, so they decided to flip it upside down. But basically, it goes from the number 1 to the top. And the way that I was taught to remember this was, if you look at the first letter of each one of these things, it can be, please do not throw sausage pizza away. So repeat that. Please do not throw sausage pizza away. Physical data network transport session presentation application. Please do not throw sausage pizza away. Please do not throw sausage pizza away. So if you repeat that a few times to yourself, you will most likely wrap your head around the organization of this, and then from there you can just kind of fill in the blanks, right? So the very first layer is going to be the physical layer, and it's referred to as layer number 1, and it deals with the physical connections between devices. So this is like the wires, right? The actual physical wires, and basically what it means to have binary data. So the zeros and ones that go through those physical wires, and that's how the communication starts, right? So if you are connected on a laptop, for example, there is no physical wire, most likely, that's connecting you to your router or your modem. So you're getting a Wi-Fi signal. But your router or your modem has a physical wire that's connected to it, that's coming from the cables outside in those beams, like those electricity beams, the big columns that are along the lines of every major street. And there's a physical wire that's running into your house that will get you access to the internet. And then from there is a Wi-Fi signal that's just distributed. So everything starts with that physical layer. And what goes through those wires is a series of binary digits, which is a bunch of zeros and ones, basically. So it can go through electrical wire, optical wire, and wireless signals as well. And all of those things technically fall under the physical layer. So in addition to the Ethernet cable, which is what you can see right here, this is what an Ethernet cable looks like. There's also the optical fiber cable, which is a much thinner version of this, and it actually has glass that goes through it, and you don't want to bend that in a sharp layer because you'll break the glass and then you won't be able to get your connection. So the optical fiber cables, fiber optics, are much more sensitive than these types of Ethernet cables, and they actually are much faster. And then so you have the Wi-Fi radio bands as well, which goes from 2.4 to 5 to 6 gigahertz of data that can transfer through those things. And if you have a 6 gigahertz band, obviously you have a much faster internet connection than a 2.4 gigahertz band. And usually when they connect your Wi-Fi for you, you at least have the option of 2 of these things if you have a decent Wi-Fi internet service provider. But that's basically it for the physical layer, right? And then we have the data link layer. The data link layer is what transmits the actual signal, right? So the data link, otherwise known as layer 2, represents the protocol that enables data transfer between nodes on the same network segment. So let me actually show you something that kind of makes this a little bit easier to understand. Okay, so I basically found this image by just Googling routers, switches, and modems. And this is what it's one network. This is representing one specific location. We can call it a floor, we can call somebody's apartment, so on and so forth. Now, most people don't actually have a switch. This is what this thing represents in the middle. And then each one of these dots that you see right here would have an Ethernet cable that's connected to them, and then it runs from that to the TV, to the recorder, so on and so forth. So most people in a home network don't have a switch. Most people in a home network will have either a modem and a router, or they'll have a router that has the modem connection in it. So typically what happens, you get your internet from your internet service provider, they hardwire an Ethernet cable or a coax cable that will go from the outside world and connect to your modem, and then the modem will have the Ethernet cable that connects to the router, and then the router will typically send out the Wi-Fi signal for all of your devices. In the modern world, most people don't have an Ethernet cable that connects from their router to their computer. You can have that. That's actually not a bad thing to do because it gives you a stronger, more persistent connection. But in the modern world, most people don't have that. In our home network, we don't have that. We have a really good router. It's very secure. It has its own firewall and everything like that. But it also acts as the modem. And then that sends the data out to the various devices that are inside of our house, all the TVs and the laptops and the computers and all of that stuff. And this is all considered to be the part of the data link layer. These devices being in the same network as they communicate with each other, this is all done through the data link layer. And the way that they communicate with each other is not through the IP addresses, because technically they're still in the same network. So they more communicate with each other through what's called as a MAC address, which is the media access control address. And the MAC address is the physical address for the device. And then there's something called the ARP protocol, the address resolution protocol, that we'll talk about in the next video, that will show you the translation between the MAC address to the IP address and how devices on the same network actually find each other via the MAC address and the IP address, so on and so forth. So this is essentially data link layer 2, right? So data link layer is layer 2. It's the layer right after the physical layer that gets the wires into the network. And then this is the way that the devices on the same network, so this is like the big thing, the big piece that you have to remember. Data link layer takes the devices that are on the same network and connects them to each other, right? Helps them communicate with each other. And there are certain protocols. So this is the IEEE code for Ethernet, which is 802.3, and then there's the 802.11 that represents the Wi-Fi, and these are just standards. So if we were to go look at this one more time, IEEE Institute of, I think let's see, stands for, it's a standard, but let's see what it stands for. So Institute of Electrical and Electronics Engineers, okay? And so this institute has the standards that we would use to make sure that everything is set up properly in networking. So for example, if you do 802.11, this is the standard for Wi-Fi. So this is the set of standards that define the physical layer and medium access control protocols for wireless local network communication. So this is Wi-Fi standards for that organization, which is the Institute for Electrical and Electronics Engineers. Okay, we can call it IEEE, which is probably an easier to, instead of saying IEEE or whatever, we're just going to say IEEE. But that's basically it. And the IEEE has a bunch of different standards. It's just that for the purpose of this video and this conversation, we're more interested with the Ethernet standards as well as the Wi-Fi standards. And the Ethernet standards are the ones that typically talk about the physical connection and then the connection of that to the data link layer. And the data link layer is what starts connecting to the actual Wi-Fi, the wireless connection, and the way that that links to our next layer, which is going to be layer 3, the network layer. So this is just an example that what you need to see is of what a MAC address looks like. So this is a unique MAC address that belongs to, I don't know what type of device this belongs to, but this is basically what a MAC address kind of looks like, right? So we expect to see 2 MAC addresses in each frame in a real network communication over the Ethernet or Wi-Fi. And this is what it looks like as far as the connection is concerned. So we have the destination that's in yellow, we have the source that's in blue, and then the remaining bits show the actual data that's being sent. So in this particular case, I mean, it doesn't really zoom in that much on it, but we can actually kind of just zoom in this way. So you can see these portions right here. These are all ones and zeros. So this is the binary. And then this portion right here, this is the hex code, hexadecimal code. And the yellow right here is the destination. The blue represents the source. And then over here, the yellow is the destination and the blue represents the source. And that's what it looks like when you're talking about a specific Ethernet or layer 2 connection in this situation, which is connecting to the CloudNet device, so on and so forth. So this is a screenshot of Wireshark, and we're going to be talking about Wireshark as we go further along inside of this module. And it's a really powerful tool, a very useful tool for sniffing network traffic, and it's free, which is one of the things that I love about it so much, which makes it very easy and convenient for people who want to become hackers to become hackers or network administrators. You can just download free software that is an industry standard. Like, everybody knows Wireshark. And if you don't know Wireshark, then you can't call yourself a security person. So let's talk about layer 3. Now, layer 3 is where the data link layer connects to the actual internet. So the data link layer is data on the same network, right? Data link layer is on the same network in the same location. The network layer is concerned with sending data between different networks. So in more technical terms, it handles the logical addressing and routing, basically finding a path to transfer network packets between diverse networks. So what you're watching, this video that you're watching, is basically a bunch of data packets that are being sent to you from the YouTube servers, and that's being done from their location of their server to your device. So your laptop, your computer, whatever, your phone. That's being sent from them to you through the air, right, through the internet, and it's being sent via these little packets, and it's being sent through the network layer. In the data link layer, we gave an example of one company office with 10 computers in the same office, which we didn't really talk about. I kind of skimmed over that. But let's say that so if the data link layer is connecting all those computers in the same office, which is what this is right here, right? So we have these computers and these devices that are in the same location, in the same office. They're being communicated via the data link layer. If the company has a bunch of different offices across different cities or countries or even continents, then the network layer is responsible for connecting all of those nodes, all of those computers to each other. So this is what that potentially looks like. You have computer A that's in one location, you have computer B that's in another location, and then these are all individual routers. So a packet will go through this router and then maybe this router and then come to this router and then connect to this person, or maybe they'll go from this router to this router and directly just go there because that's the fastest route possible. But sometimes maybe this one is down, so it has to go. So there's different routes that a packet can take depending on what is going on in the world and inside of the network communications devices that are available for all the routers that are available. So that's basically what it looks like. So it'll go from its own computer it goes to the local router that's inside of that room. Then it'll bounce and go to a variety of other routers across the world, which are usually provided by the internet service provider. And then it'll end up at the router for this computer that's inside the room with that computer. And then it'll send it to the actual computer. That's typically what the network layer looks like. So you have examples, and we already talked about the examples for this already. So I already talked about those examples. So the examples of the network layer would be things like the Internet Message Control Protocol or Internet Control Message Protocol, ICMP. We have the Internet Protocol, which is IP. You have Virtual Private Networks, VPNs, and of course IPsec or IPsec, and then SSL and TLS via VPNs. These are all examples of the network layer protocols. And then we have the transport layer. So the transport layer actually enables the end-to-end communication between applications on different hosts. So now it's going from my email provider to your email provider. That's the application. And the transport layer connects those two applications together, right? So it enables the communication between those running applications. Maybe it doesn't connect them, but it allows them to communicate with each other. So your web browser, for example, is connected to my web browser, is connected to TryHackMe over the transport layer, which is going to come up in a little bit. And or actually we're literally on the transport layer. So the web browser is connected to TryHackMe. Mine is connected to the TryHackMe web server over the transport layer, which supports various functions like the flow control, segmentation, and any error correction that needs to take place. And there are two very key protocols for the transport layer, which is the TCP, Transmission Control Protocol, that requires the verification of a connection. And then you have the UDP, the User Datagram Protocol, that does not require the verification of a connection. So what you're watching right now through a video from a streaming platform, which is YouTube, most likely is using UDP, which is sometimes why the quality of the video isn't perfect, because sometimes it'll be pixelated because the internet connection is kind of lagging, or you're not receiving all of the data packets. So it's not as important to get a perfect connection through the video streaming platforms. And you've probably recognized this in a lot of different, and it happens even with Netflix or with Amazon Prime or something like that. Any kind of video streaming uses UDP because it's quicker, so it can send data packets faster, but it doesn't require the confirmation of a connection. TCP requires the confirmation of a connection. We'll talk about that in more detail later. But all of this basically happens on the transport layer. So the transport layer, if you can think about the network layer connecting the actual computers to each other, the transport layer connects applications to each other. So we have my web server, for example, or my web browser connecting to the TryHackMe web server. You have your web or your YouTube application or your YouTube web browser that's connecting to the YouTube server. So that's all being done for between applications, the communications between applications. And then what happens is that once that communication is permitted and it's done through either of these protocols, then a session is generated. When a session is generated, it establishes, maintains, and synchronizes that communication between the applications. And it can mean initiating communications between applications, negotiating the necessary parameters for the session. It can also mean that data synchronization ensures that the data is transmitted in the correct order, and it has recovery in case of transmission failure. So imagine you close this browser, or accidentally something happens that the browser crashes. When you come back to this video, most likely it's going to pick up from where it left off, because you had a session that was generated for viewing this video, and then YouTube allows for those sessions to just be recovered so that you don't have to start from the beginning. And if I'm uploading a video to YouTube and something happens and before the upload is completed and that crashes, when I go back, or maybe like my external drive gets disconnected or something, when I go back to continue that upload, it'll allow me to continue from where I left off, and it won't restart the upload from the very beginning. I just basically pick up from where I left off, and that's very, very useful in recovery situations. A network file system, for example, is a very, very important one. So it's basically a file system, a file share that's being accessed over the internet connection. So somebody that's working in a remote location that needs to access this thing. So they would do a remote call to the file system. And then once they have their established connection, that session is generated, and then they can access the data, ensuring that it's actually transmitted in the correct order. And then if there's any kind of failure, they actually can recover that session. And then we have the presentation layer. So the presentation layer just makes sure that the data is delivered in a way that the application that you're using can understand it. So this is responsible for basically the data encoding, compression, or encryption of the data. So for example, you have the ASCII encoding or the Unicode encoding. And an easy way to understand this is that if you have an image that you're sending through an email, you can have JPEG, GIF. I pronounce it GIF. I don't trust anybody who pronounces as a GIF. And then you have the PNG. So these are a variety of different ways that an image can be encoded, right? And they serve different purposes. So for example, if you want a transparent background, you have to have a PNG file, because GIF or JPEG typically doesn't support transparent backgrounds. And then GIFs are usually for animated images, so you can't have PNGs who are animated. So if you have an animated image, it's a GIF typically. So it's different types of encoding that's available for these things. So even though it's hidden from the user's email client, we use the multi-purpose internet mail extension to attach the file to the email, and then MIME encodes a binary using 7-bit ASCII characters. So what you see if you're capturing that email is not the actual image, you just see ASCII characters, which is another version of encoding. So this is what's kind of interesting and important to understand, is that the presentation layer really has nothing to do with the data visually being presentable. That's for the application to present. The presentation layer just makes it so that the encoding, compression, and encryption, and then ultimately that going through the session layer and the transport layer, it makes it so that all those things are actually possible. And then you get to the application layer that actually views it, right? It makes it viewable to you. So it could be through your email. HTTP protocol is to request a file, submit a form, upload a file. You also use the HTTP protocol to connect your Gmail address and receive your data. And then there's the secure version of it, which is HTTPS. And then you have a lot of layer 7 protocols like file transfer protocol, domain name services, POP3, SMTP, and IMAP, which are all used for email. So you don't need to memorize these things. There's literally thousands of ports and protocols, and I don't think anybody's expected to remember that stuff unless you are just a genius with remembering things, which I'm not. I'm not good at data retention, but I'm really good at knowing where to find information. And that's the big thing that is important in a lot of environments, just knowing how to find the information and access that data. So that is what we got for the application layer. So just going back to the top real quick, just so I can show you this, right? So, you start with the application. That's how you interact with your phone or your computer. The application then sends that data, those data packets, to the presentation layer, the session layer, the transport layer, the network, the data link, and then the physical layer. It goes through all of this just to leave your house, to leave your network. And then it travels over the internet and then ends up at where it's supposed to end up. And then it goes through the physical layer, the data, and it just reverses until it gets to the application layer. So let's say that's for YouTube. You're trying to access a video on YouTube. You go and you submit your search query, you find the video, and then you click on the video. And all of that stuff that you're doing is going from your application layer all the way to the physical layer, and then ending up on the other side on the physical layer, going to the application layer, and then the YouTube server sends the video from their application layer to their physical layer, and then that comes back to your phone or your laptop, connects to your physical layer, then comes to the application layer so that you can actually play the video and watch the video. And that happens in a matter of seconds, not even a second sometimes, right? So this is what's interesting to understand. And this is what's amazing about the modern internet, is that it's so freaking fast. And it goes through all these different layers in a fraction of a second. And then you get access to your video and you get to do whatever the hell that you want to do, right? So This is just a little cheat sheet that you have available for you. So if you wanted to look at what these things are, but then there are so many different cheat sheets. So we can always go to Google right here and then actually just type in the ISO cheat sheet, let's say ISO cheat sheet, and then you'll get a bunch of different cheat sheets that will make it. And some of them are really detail oriented. Some of them are just very, surface level, kind of like this one. So if just depending on how much detail you want, there's a lot of stuff that's available for you that you can skim through so you can wrap your head around this whole thing. I like visuals that make me kind of just get everything in one image. And that, I think, is one of the big things that's also really powerful with the internet nowadays, that you can just basically click on something and you will get the visualization of a complicated concept all in one image. And then that way you can really easily wrap your head around it. So just find something that is appealing to you and save it for yourself. And that's how you can remember these various letters. And obviously, always remember, please do not throw sausage pizza away. Okay? Please do not throw sausage pizza away. That's how you can remember these layers. Okay, so which layer is responsible for connecting one application to another? So we talked about end-to-end connection of applications, and that was done through the transport layer. That's where end-to-end connection of applications happens, and it's done through UDP or the TCP protocols. Which layer is responsible for routing packets to the proper network? So this is where it goes from the data link layer to the network layer, and it goes from network to network, and packets are sent through routers. So if you can recall the image that we had over here, these are routers, right? So it goes from this guy's network through routers, and it gets routed to this guy's network, and that's done through the network layer. And then in the OSI model, which layer is responsible for encoding the application data? And that's layer 6 that we talk about over here, which is data encoding, encryption, and compression. And then finally, we have which layer is responsible for transferring data between hosts that are on the same network segment, which is what you see over here. This is the same network segment, and that is done through the data link layer, which is layer 2. So that's what we have for the ISO model. And now let's look at the modern version of this, where we actually, where network administrators and network engineers actually implement this into the real world. And that's done through the TCP/IP model. The TCP/IP stands for Transmission Control Protocol and the Internet Protocol. So TCP, Transmission Control Protocol, and then IP, Internet Protocol. This was developed in the 70s by the Department of Defense. And they did it mainly because they wanted to make sure that they have a process to manage something if it ever happened where they got a military attack for whatever. It allows the network to continue to function as it's a part of an out-of-service network, for example. It's possible due to the design of the routing protocols to adapt as the network topology changes, right? So you have a variety of different network topologies, which we've talked about previously. And once you kind of go through that, you can understand that the routing protocols still need to be consistent, even if the topology of the network changes, meaning the physical layout of the network. Network topology refers to the physical layout of the network, and the data still needs to transfer, and it needs to route properly no matter what the physical layout of the network is. Now, what happens is that because of the update of it, if we do ISO versus TCP IP, we can see that this is actually, they've combined the two, or not combined the two, they've combined multiple layers. And what it looks like is instead of having 7 layers, we actually have 4 layers. So let me actually kind of zoom out of this so you can see this a little bit better. So instead of having 7 layers, you actually have 4 layers. And the first 2 layers right here, the physical and data link, go into the network interface. Then you have the network, which is also the network, but they call this the internet layer. Transport is still transport. And then the 7 up here, 7, 6, and 5. So session, presentation, and application are falling all under the application layer of the TCP/IP. So these 7 have now been turned into 3. Right? Or excuse me, 4. Sorry. These 7 have been turned into 4. The data link and physical layers have been combined together. Network is still network, or otherwise interchangeable, is called internet. So either network or internet layer. You have transport, which is still the same. And then session, presentation, and application are all under the application layer, because technically they are all done through the application. So Google Chrome will generate a session. It will go through the encoding of the data to make it presentable, and then it will actually present it to you via the application Google Chrome, and it's all done under the application layer. So when you look at it like that, this is basically what it breaks down to. Now, this is not as user-friendly as the image that you just saw, because it's it is basically still the same. So you have the application, presentation, and session layers, which all fall under the application layer, and the protocols are still the same, right? HTTP, FTP, Telnet, so on and so forth. Transportation is still the transport layer. Network layer is the internet layer, which is ICMP, IP, so on and so forth. And then data link and the physical layer all fall under the link layer, which is Ethernet and Wi-Fi. There are versions of this that actually turn it, instead of 4 layers, into 5 layers. And basically what they've done is that they've added the physical layer. So they've added another line item for the physical layer, so to differentiate between this. But this, the application session and presentation are also still the application layer. The transport layer is still the same. Network is still the same. It's just that these last two right here, or the first two, I guess we can call them, these two have actually been separated. So you have the link layer as well as the physical layer. And that was something that was done by, by Kouros and Ross in their book, Computer Networking, a Top-Down Approach. And I guess it's important enough for them to mention to us. So most places, though, they worry about the 4 layers of TCP/IP. They're not considered about this version where it has 5 layers. As long as you know what the layers are and how they break down, that's basically the most important part of this whole thing. So to which layer does the HTTP belong in TCP/IP model? And that is the application layer, because HTTP, again, is application, presentation, and session. That's all falling under one layer inside of the TCP/IP model. And then how many layers of the OSI model does the application layer actually cover? And that is 3, right? Again, application, presentation, and session, all combined into one layer in the application model, or the application layer of the TCP/IP model. So now, let's talk about IP addresses and subnets. When you think about an IP address, you most likely recognize this as an IP address or this as an IP address, and this is considered a IPv4 IP address. Now, what happened is that there's approximately 4 billion types of, or 4 billion different unique IP addresses that can come up with IPv4, and across the world, there are way more than 4 billion devices. So ultimately, it runs out. But there has been some interesting things that internet service providers have done so that people can still deal with IPv4, but it eventually graduated into becoming IPv6, which is a very different type of formatting. And because it offers more positions in it and more variations, it can now generate many, many, many more unique IP addresses if you use IPv6. But for the most part, in the world today, we are still dealing with IPv4 formats of IP addresses. The main reason for this is because every host on a network needs a unique identifier so that the other host can communicate with it. Without the unique identifier, the host can't be found without ambiguity, meaning we can't know for sure what the address of a specific device is. So if you think about it as the home address, the postal address of a person, your postal address will allow the UPS or USPS or whatever the mail service is to actually find you specifically without ambiguity, right? Otherwise, your package is going to get delivered to somebody else. You won't be able to shop online. So that's what's important about IP addresses in the world of the internet, is that you are found specifically. And there's IPv4, obviously we talked about IPv6 as well. And the big thing that's very important to understand about IPv4, and this is where the details of subnets become a very important detail. It's not that confusing. I'm going to try to make it super simple for you, okay? The big thing is IPv4 addresses are 32 bits and they contain 4 octets. So if you can consider an octet like an octopus, right? If you can consider an octet to be 8 bits, If you divide 32 by 8, that means you have 4 octets, okay? Each one of these positions, so everything that's separated by this dot in the middle right here, that's 1 octet. So you have octet 1, octet 2, octet 3, octet 4. It goes from 0 to 255. Each octet goes from 0 to 255. However, the IP address itself will not actually include 0 or 255. Why? 0, so 192.168.1.0, is the network address. And then 255 is the broadcast address. So the IP address that your laptop will actually get is going to be between 1 and 254, okay? So you will never find an actual IP address of a machine that will be ending in 0 or 255, because the 0 is the network's address and then 255 is the broadcast address, and every machine on that network is going to have the same network address and the same broadcast address, but the unique IP for that machine is going to be from 1 to 254, okay? Hopefully that made sense. Now, what we need to understand is that there's something called a subnet, and the subnet is what kind of makes things accessible for either a small environment like your house or a business environment that has thousands of employees and thousands of machines, okay? So first you need to know how to pull up your configuration. So if you're using Unix or Linux, which, Mac OS is technically Unix, you would use ifconfig, and then it pulls up your IP data. And so in this machine, on this particular machine, the IP address is this, right? Ends in 89. The network mask is this, and I'll explain what this means in a little bit. And then we have the broadcast address that ends in 255, right? And then the actual network address, I don't think is on here, but the network address would be the one that ends in 0, okay? But the broadcast address, as we established, ends in 255, okay? So this is the IPv6 address. Notice how this is such a very different view than this one right here. And if you can imagine, because there are so many different variations, so this one actually has letters in it, right? So this one is only numbers. This one actually has letters. And so when you look at this, first of all, it's separated by 5 different chunks of data, and then there's letters in it, which means that you can have many, many more variations, billions. I think it's like centibillion, something. I don't know what the word is, but there's so many more billions. There are many more billions variations of the IPv6 than there are of the IPv4, okay? But this is basically what the output of ifconfig looks like. There's another command that allows you to look at it, which is the IP, and then AS is the address show. So AS stands for IP address show, and then that basically shows you a very similar output. Now, what we need to understand is mainly, because the output is similar for the most part. So it has the IP address still, but and then we have the IPv6 as well. But the difference here, the key difference here, is the subnet representation is different in ifconfig, because it actually shows you the network mask, which is the subnet over here like that. Over here, the subnet is represented by the /24. And the reason why that's important, okay? So going back to the concept of octets. So if we think that this is 8, this is 8, and this is 8, if we do 3 times 8, that means there's 24. So that's what the /24 represents. Meaning, this last position is the only position that will get filled in. So on this subnet, there can be between 1 to 254 addresses that can exist on that subnet. Now, the reason why this is important is when you go into the enterprise environment, their subnet is probably going to be 255.255.0.0, which means what? If we do 8 times 2, it would give us a subnet of 16, meaning that 16 positions, 16 bits on this are not going to be filled in, and then the other 16 will be filled in. In this one, 24 is not going to be filled in, and then the last 8 is going to be filled in, okay? That's how you can kind of understand this. When you see /24, that means 24 bits will not be filled in. They're going to stay exactly the same. So you see 192.168.66, 192.168.66. So that portion is not going to change. However, the last bit, the last 8 bits will actually change. And if you have an enterprise environment that has these two that are not going to change, but the last two will change, now you have 254 times 254, which ends up being 65,000 plus addresses that can be assigned on that network, which is way more conducive to a enterprise network in a business environment, because they have way more than 254 IP addresses. Most people, because they have their cell phone and their laptop and their desktop for work, the average employee will take up 3 IP addresses. You know what I'm saying? So if you have one person taking up 3 IP addresses, for the most part, you can probably have maybe around 100 employees, a little bit less. So let's say 80 employees that will comfortably be on that network. Anything more than an 80 employee environment, they need to have a larger subnet, because they just need way more than 254 addresses, right? So that is why a subnet looks the way that it does. And that's what it is. So if you can kind of just wrap your head around the fact that this piece, the /24, is representing the number of octets that will not be filled in. So if you divide it by 8, that means 3 positions are not going to be filled in. And then if it's 16, that means these 2 positions are not going to be filled in. And if it's 8, which, I mean, I can't imagine that there would be 8, that means that this first one isn't going to be filled in. These last 3 will actually be changed. So that's kind of what you can think about in that kind of an environment. So now that we have that out of the way, let's talk about private addresses. Now, we're going to talk about network address translation in a little bit, but what's important to know is that any IP address that starts with a 10, 172, or 192 is a private IP address, and this is by the RFC, which is the Request for Comments, a publication that's for the Principal Technical Development of the Internet Engineering Task Force, okay? That's, again, kind of like extra information that you really don't need. But you do need to understand that anything that starts with a 10, anything that starts with a 172, or anything that starts with a 192 is a private address. So for this lab that we're using, we're going to actually have this machine right here, which is a target IP address that was created for my virtual machine, and it starts with a 10, which means that this is actually a private IP address that belongs to TryHackMe. And when I'm done with this session, when I terminate this is going to go away, and this IP address will no longer be valid. Okay, so hopefully you can kind of wrap your head around this and understand how this whole thing works out. So remember, if it starts with a 10, 172, or 192, these are private addresses. That's very important to understand. Now, we presented earlier an analogy using public IP like your home postal address. A private IP address is different. The original idea is that it cannot reach or be reached from the outside world. It's like an isolated city or a compound where all the houses and apartments are numbered systematically and can actually exchange mail with each other, but they cannot exchange with the outside world. For a private IP to access the internet, the network address translation is what is used to create a public IP address so that it can actually communicate with the outside world. We're going to talk about this later on in this series, so I'm not going to jump too deep into it. But we do need to understand that if it starts with a 10 or 172 or 192, for the most part, that is a private IP address, okay? And then we have the routing concept. So imagine that the router is your local post office. You send your packets or your data or your packages and mail to the post office. The post office will process it. It'll send it to maybe another post office, and then it'll send it to another post office, and finally end up in the final post office for where it's supposed to be delivered to. And then in that place, it's going to send it to the actual person or the entity that's supposed to receive it. So you hand them the mail parcel, they know how to deliver it. If we dig deeper, you might mail something to an address in another city or a country. The post office will check the address and decide where to send it next. For example, it is to leave the country. We expect the central office to handle all of the shipments abroad. In technical terms, a router forwards data packets to the proper network. Usually, the packet passes through multiple routers before it reaches the final destination. The router functions at layer 3, which is the network layer, or the internet layer, inspecting the IP address and forwarding the packet to the best network router so that the packet gets close to its destination. So it goes from this, goes to this router, then to this router, and then this router, and then this person, or this router, and then this person. Does that make sense? So it goes through routers. Routers route. That's how you can kind of remember that, right? So here we go. Which of the following IP addresses is not a private address? So starts with 192, it's all good. Starts with 10, all good. 172, all good. If it starts with a 49, that is a public IP address. And that is the answer. Which of the following addresses is not a valid IP address? So remember, it needs to go from 1 to 254. Every single position can go from 1 to 254. So if it's going to 305, that means that this is not a proper IP address because it passed 254. It can be on 254, it can be 250, it can be anything between 1 and 254. If it goes past 254, that means it is not the IP address. So that is actually the right answer. So let's talk about UDP and TCP. So if we go back to the transport layer of how data gets transported, we can talk about, or we can remember that the transport protocols are UDP and TCP. Now, UDP, the user datagram protocol, allows you to reach a specific process on the host, very similar to TCP. It's a connectionless protocol, meaning that you don't need any kind of connection to be fully established, right? It doesn't even provide a mechanism to know whether or not the packet has actually been delivered, right? Which is why if you're watching a video and sometimes it doesn't come through at its full quality, it's because UDP doesn't care, right? It doesn't give a darn. I was about to start cussing. It doesn't care whether or not the packet's been delivered. It just sends the packets. And whether or not you deliver or whether or not you receive it, it doesn't care, okay? So the IP address identifies the host. We need a mechanism to determine the sending and receiving of that process, and it can be done by port numbers. A port number uses 2 octets, consequently, it ranges between 1 and 65,000 and change. Port 0 is reserved. So the number 65,535 is calculated by the expression 2 to the 16th power minus 1. Again, a lot of detail. You don't necessarily need this unless you're just going to become a network wizard, right? A real life similar to UDP is standard mail with no delivery confirmation. So there's no guarantee that the packet has been received successfully, similar to the case of sending a parcel using standard mail with no confirmation of delivery or tracking number or anything like that. In the case of standard mail, it means a cheaper cost than the mail delivery option with confirmation. In the case of UDP, it means better speed than the transport protocol that provides confirmation. So what if you want something that actually acknowledges received packets or provides confirmation? Then you go into TCP. TCP is a connection-oriented transport protocol. It's not connectionless, right? It uses various mechanisms to ensure reliable data delivery sent by different processes on the host. Like UDP, it is a layer 4 protocol because it's transport. Being connection-oriented, it requires the establishment of a TCP connection. So this one actually really cares that the data has been delivered, right? In TCP, each data octet has a sequence number. This makes it easy for the receiver to identify lost or duplicated packets. The receiver, on the other hand, acknowledges the reception of data with an acknowledgement number specifying the last received octet. And in this case, we need something called the three-way handshake to be actually completed. We also call it the TCP handshake, but it's basically 3 shakes of hands, or 3, I don't know. It's a 3-way handshake, whatever. There are 2 types of flags that we use, which is the synchronized packet and the acknowledgement packet. So the first one that's sent out is the SYN packet. The next one is the SYN acknowledgement packet. And then the final one is the acknowledgement packet. So you, as the person requesting, the client, you as the client, initiate the connection and you send a synchronization packet. And you say, hey, I'm just trying to find the connection to this. Here's my initial sequence number. The server will respond to your to your synchronization request by giving you a synchronization acknowledgement. So I acknowledge that you're trying to synchronize with me. And then it adds the sequence number randomly chosen by the server. So you send your sequence number, it sends its sequence number, And then at the final stage, you send the final acknowledgement saying, yes, okay, great. I acknowledge that you're acknowledging my synchronization, and I will send you my final acknowledgement, which means if this has been sent, if you see an ACK package, that means that the connection is actually been done. And this is what the visual looks like. Client sends the synchronization. Server sends, okay, I acknowledge your synchronization request. Client says, cool, I acknowledge your acknowledgement, and we are officially done. So similar to UDP, TCP identifies the process of initiating or waiting, which means listening, for a connection using port numbers. So there are TCP listening, UDP listening ports. They both connect via port numbers. And a valid port number ranges from 1 to 65,535 because it uses 2 octets and port 0 is reserved, So, which protocol requires a 3-way handshake? That would be TCP. What is the approximate number of port numbers in thousands? It's 65,000. And this 2-octet thing, so if you remember, if we go at the subnet example and we have 255.255.0.0, that means the last 2 octets are now reserved for that communication. And if you do 255 times 255, it ends up being 65,000 and some change. So that's basically how you get that. So let's talk about encapsulation, and then we can go into our example at the very end where we run some of these things practically, and then we can talk about our closing notes and our conclusion, and then we'll be done. Encapsulation refers to the process of every layer adding a header and sometimes a trailer to the received unit of data and then sending the encapsulated unit to the layer below. So the best way that I can explain this is through a visual, and I hope that I can find actually a really good one for you. So let's see what we can find as an example here. Okay, so unfortunately, I wasn't able to find an example that I was taught that I was looking for. But one of the best ways to actually think about it is what the term encapsulation really means in general. So encapsulation in general means you take something and you put it inside of a capsule. So you take whatever this is a programming example where they're taking variables and methods and putting it inside of the capsule to create a class, okay? But in general, this is the networking example where you have the actual data, and then on the link layer, you have the data, and then on the internet layer, you have the IP header and the data, and then on the transport layer, you have the UDP layer as well as the data, and then you have the application layer, which is the actual data. And all of these things are encapsulated, right? They are put inside of one giant packet, or, you know, giant, quote unquote. And the way that that works is that that's sent off, and then when it's received on the other end, it's decapsulated, so it's opened up, and then each one of those headers tells the router where the thing needs to go. So it starts with when the user inputs the data that they want to send into the application. So you write an email or a message and you send the button or hit the send button. Application formats the data and starts sending it according to the application protocol used and using the layer below it, which is the transport layer. So it'll first start with the application layer, which is this thing right here. Whoops. This thing right here. So let's open this in an image. So it starts with the top layer, which is the application layer. You send your data. The data will go to the transport layer, and the transport layer will add its header saying that I'm going to send this using the UDP, the user datagram protocol. I'm going to send it using this protocol, and then here's the data, okay, in the UDP format. And then it's sent to the internet layer, which is the network layer. And then it has the IP addresses, meaning that it's coming from this source IP address and it's going to go to this destination address. And then here's the data, right? And then you have the final link address, which is going to take it from the frame itself, and it's going to add its header as well as the footer so that it can actually go to your physical router so it can leave your network, right? Because remember, it's going to start from your application, it's going to go down the line until it hits your router and leave your house, leave your building. And then from there, it'll land on the other side, and it will first be received by the link layer. Then it's going to be opened up by the IP address, and it's going to say, oh, it's supposed to go to this computer. And it's going to be opened up by this, and then it's going to finally decapsulate or open up the final encapsulated packet so that you can actually get the data that you wanted, which is the message, right? So the transport protocol segment or datagram. So the transport layer such as TCP adds the proper header information and creates the segment if it's TCP or datagram if it's UDP, and this segment is sent to the layer below it. The network packet, which is the network layer, and adds the IP header to the receive segment or datagram, and then it'll send that packet to the layer below it, which is the data link layer, and then the Ethernet or Wi-Fi receives the packet and then sends the proper header to create the frame. So if it's on the link layer, it's a frame. If it's in the network layer, it's a packet. And then if it's in the transport layer, it's either a segment or a datagram. And then finally, it ends up as the message or the funny cat GIF that you wanted to send to your girlfriend or something like that. So we start, again, we can look at it like this, right? We start with the application layer, then we send the application data and attach a TCP or a UDP header. So if it's a TCP, it's a segment. If it's UDP, it's a datagram. And then it's going to go back down to the IP layer or the network layer, which is going to take the application data, the TCP header, and then the IP header, and it's going to add that to it, which includes the source IP and the destination IP, so where it's coming from and where it's going. And then we have the Ethernet final layer, the physical layer, the link layer, which is going to take all of that information and then encapsulate it. So each process is basically getting more and more encapsulated. So imagine this is an envelope, then it's going to be placed inside another envelope, then it's going to be placed inside another envelope, and then it's going to be placed inside another envelope so that it can get sent out. That's what you can look at it. So this is what we can think about on the TryHackMe example that we have here. So on the search page, you enter your user search query. So I go up here, click on this, and I search for something in there. I'm so zoomed in right now that I can't see everything. I'm like, I think 250x or something. I'm really, really zoomed in right now. So it'll go from the search query, right? Then the browser, using this protocol, prepares the request and pushes it to the layer below it, which is the transport layer. Then that layer needs to establish a connection via the handshake between my browser and the TryHackMe web server. After that connection is made, it can send the request containing what I wanted to search for. And then each one of those segments created is sent to the layer, which is the internet layer. And then, so again, I'm putting it into the browser for my application. The browser is like, okay, I'm going to use a secure method to send this over. And then I'm going to establish a connection via the transport layer so we can actually send it to the IP, to the router that's inside of my house. And then the router is going to say, oh, okay, this is the IP address that it's coming from. And then it's going to go to the IP address of the TryHackMe server. And then the packet reaches that router, the laptop delivers it to the layer below, which is the actual data link layer, which is going to be that physical wire that's connecting my router to the pole outside of the building, okay? And then the router removes the link layer, header and trailer, inspects the IP destination, all that stuff, and then routes the packet to the proper link. And then when it lands on the other side, each router will actually repeat this process until it's finally gone to the TryHackMe server, which will unwrap the entire package and be like, oh, okay, this is what the guy wanted. Let me send it to him. And then the web server on that side will do the same exact thing and then send it to me. And then my wire receives it, sends it to my router. The router sends it to my computer, and then the computer unpacks it, and we get the data that we want. So on a Wi-Fi, within what will an IP packet be encapsulated? So on the Wi-Fi, it's going to be inside of a frame, okay? And then what do you call the UDP data unit that encapsulates the application data? That's the datagram. What do you call the data unit that encapsulates the data that's over TCP? That's called a segment. And that's all she wrote. So let's jump into Telnet and actually use this machine that I started about an hour ago. So let's get into it. All right, so what we are going to do is we're going to use the teletype network protocol, which is called Telnet. And it's used for remote terminal connection. And you can connect to a variety of ports. The ones that we're going to connect to is port 7, port 13, and port 80. Now, by default, port 7 is not accessible on any network because it's not secure. Neither is port 13. They're not secured ports, they're not secure protocols. So in most environments, other than this controlled environment, in most other environments, you're not even going to see these as open ports. The HTTP server, which is for web servers and web pages, will most likely be open. But what's going to happen is that it's going to be followed with an HTTPS port. So there's port 80, which is HTTP, and then HTTPS is port 443, which is the secure connection of HTTP, which is encrypted, right? But in this particular case, we're literally connecting to all of the insecure versions of these things. Before continuing, we need to make sure that echo and daytime servers are considered security risks, should not be run, which is the 7 and 13. However, we started them explicitly to demonstrate communication with the server, yada, yada, yada. So the way that you use Telnet is just type Telnet, the IP address, and then 7, meaning the port that you want to connect to. So in this case, this is what the echo service does, is that you just connect to it and then you type hi and it says hi. You say, how are you? It says, how are you? Bye, bye. So it literally just says everything that you say and it just prints it back to you. And if you want to close, you would do controlled and then the closing square bracket and then it close that connection. And if you want to, it'll close that connection, but then it'll pop you back into the Telnet service. So if you want to get out of Telnet, you type quit and then you close that out. And then pretty much the same thing that we're going to do with the third 13, which is the current date and time. That's all it's going to do. It's going to just spit me the current date and time, and it's going to close it immediately. And then finally, we have port 80, and I'm not going to give you that yet because I want you to see how it works. So let's just run these things real quick. So this is the IP address. So let me just copy that to make life easy here. And we're just going to zoom in on this guy right here. So we're going to do Telnet. Now we're going to right click, paste the IP address, and then we're going to close on port 7. And it says, hey, you are officially connected to this port. So if I say hi, it's going to say hi. If I say bye, it's going to say bye. So I just do control square bracket and it closes, and then I got to do quit and it'll close that for me. Then we clear that out, and then we're going to run this one more time, except now we're going to connect to port 13, press enter, and immediately gets me the date right here. Which is December 26th, because this server for TryHackMe, all of their servers is actually, I think it's in the UK. It's basically somewhere that's a day ahead of me. So they're living in the future right now. And then so I get the 26th because today's Christmas Day. It's the 25th for me. And so that's done. And then boom, it just spits me out. It just closes me out automatically. And then finally, we have the one that will be done on port 80, which is going to be our web server. Now, I am actually connected to the web server, but there's a few things that I have to do to be able to finalize that connection. And the way that we do that is we need to first say that we want to make a GET request. Let me actually, this is a better way to do this. First, we need to say GET in all capitals, space, / space, HTTP / 1.1. That's the first thing you got to do. And then you press enter. And then you have to give it the host that you want to connect to, which is telnet.thm. Then you press enter twice, and then you can actually access the server, and it'll respond to you and say, your success or your connection was established successfully, which is done with the HTTP 200 response. And then you basically, if you can access any data, you'll be able to access it. If not, it'll just automatically close you out. But there are some data that we do need to be able to answer the rest of the questions on this lab. So I'm going to actually type in those things that I need to type in. So right here, it kicked me out because I didn't do what I wanted to do, or what I should have done, I guess. So let's clear this out, and then let's do this one more time. So not 8, we want 80. Close that out again. Goodness gracious. Boom, boom. 80, enter. Very good. So we're going to make a GET request, and it's going to go to the HTTP / 1.1. Press enter, and it's all good. So host is going to be the, what was it? It was telnet.thm. There we go. Telnet.thm. Press enter, and then press enter one more time. And now you have all the data that you want. And so the questions that we have at the end is, what type of server are you connected to, which is the light TPD 1.4.63, and then what is the flag, which is THM Telnet Master. And so if we go at the bottom right here, it is what is the connection, or what is the server type, and there it is. And what is the flag? There's the flag. And just like that, we have officially wrapped this particular room. So let's go through the conclusions and the final notes, and then I will give you a couple of other stuff, and then we're gonna get out of here. It's so crazy. When I started this recording, it was light outside, and just like that, it got dark. So we're officially wrapped. This was the networking concept, so the very, very basic introduction to networking, and we did run some couple of labs here. So that was it, and that's basically all you need. The very next video is going to be episode 15, I want to say, and then that's the one that's going to be on networking essentials, and then we're just going to go deeper and deeper into networking and ultimately even get to use some cool networking tools. So that is it for this one. If you did find this video useful and you would like to get more future videos on the CySec101 pathway, as well as basically everything else that we talk about on this channel, for example, the Security Plus certification course that's going to come out in a couple of weeks, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And if you have any questions, drop a comment and let me know what your question is. I am very responsive in the comment section. And then, of course, we're going to talk about anything that you would need in a video. So if you have a really big question that requires a long response, I'll create a video in response to your comment. The CySec101 training series is a response to Darnell Knight's comment. And Darnell was literally the guy that was like, hey, could you do something introductory? I was like, you know what? That's actually a really, really good idea. And so we started this entire playlist that does CySec101 for people like Darnell. So if you are grateful for this, then you should just say thanks, Darnell, or something like that in the comments. But if you have any questions, also let me know that you have the question and I'll respond to your questions. And then, yeah, just make sure to like, subscribe, turn on the notification bell, drop a comment so that I hear from you. And of course, you get notified the next time that a video comes out. And then there's the Hackaholics Anonymous membership community, if you have not checked that out yet, which is the premier membership community for cybersecurity professionals and hackers. There are 4 tiers of benefits. Starts from the cyber supporter that they gets their own early access to content. They get their own Discord servers that get access to me directly, as well as all of our advanced members. And then it goes up to the advanced memberships, which is the Cyber Agent, Cyber Guardian, Cyber Master. They get Python automations every single month. They get live streams that happens every single month. They get exclusive content. They get exclusive downloads. For example, all of the notes and practice examinations and practice questions for the Security Plus that's going to come up. So if you want to join Hackaholics Anonymous, which I really hope you do, you can join through the link in the description below. You can go to our homepage and click the join button, or you can go to youtube.com/@HankHacksHackers/join, and you will get direct access to the Hackaholics Anonymous community. I really hope I do see you in the Discord chats. If I don't see you in the Discord chats, then at least I hope I see you in the comment section. And that's it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker / protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. Merry Christmas. Happy New Year. I hope you have an amazing 2025. We're coming on our 1-year anniversary for this channel in January 4th of 2025. So thank you for being here. Thank you for being a member. Thank you for being a subscriber. Thanks for being a watcher. And thanks for being a part of this community. I hope you got a lot out of it. Love, peace, and chicken grease. Peace. Later.